All right, you may think you know what TLC stands for, but you're going to learn something new today. It's not tender love and care, it is thin layer chromatography. And experiment 2, which I understand you have actually done before in general chemistry, we will revisit because it's such an important technique in OChem. So how does this crazy technique work? It's really fun and easy. And we're going to start with a bad analogy. Get used to it. All right, so the bad analogy is I have a kind of a mixture of some weird, let's just say, fuzzy balls that I can't separate. There they are. So what I'm going to do to separate them, stick with me here, is I'm going to let them roll down a plank that is covered with carpet. And what I hope you can see about these two little pieces of stuff, one is kind of hard and smooth, while the other one is kind of, like I said, fuzzy and has kind of these fuzzy appendages on it. So they're really quite different in their texture. All right, so I let go of them and they roll down this plank covered with carpet. And they stop at a certain time when I say, okay, stop. And it turns out that the fuzzy one, because it's all covered with carpet, or little barbs, the little barbs all get caught into the fuzzy carpet, and so it doesn't travel as far or as fast as the one that's more like a, let's say it's more like a ball bearing or a stainless steel ball. So, I mean, if I wanted to redo that exciting animation, you can see the ball bearing goes a lot faster, and in that same period of time, the little sticky thing doesn't travel as quickly. That's what TLC does. It's just on a much, much smaller scale. You see, if I just take that plank and tip it up vertically, it's just like a TLC plate. This blue thing is just the glass backing, and that tiny gray layer is something called the stationary phase, the adsorbent. And that is like the carpet. So, when I roll my mixture of stuff, one goes faster than the other. That's exactly what happens in TLC. My plank of carpet is in fact a TLC plate. I started out with my mixture of things down here. They traveled up the plate instead of rolling down the plank, and because one travels faster than the other, it ends up further up on the plate. The one below it is the slowpoke that sticks to the plate and therefore doesn't move as far as fast. All right, so the carpet is the adsorbent, aka the stationary phase, and in our organic chemistry labs, we're almost always going to be using silicon dioxide, SiO2, as our stationary phase. The gravity that let the balls roll down the carpet in TLC, it's not gravity. In fact, it's a developing solvent that pulls the balls, the samples, up the plate. The developing solvent is also referred to as the eluent, and it's the mobile phase. In our usual cases, we're going to be using a mixture of ethyl acetate and hexanes. In the analgesic lab, since we're using some really polar compounds, there'll be a touch of acetic acid in there too. All right, so what you need to know is that the adsorbent in this experiment is always more polar than the developing solvent that is pulling the compounds up the plate. So that means your samples are going to stick to the plate, and we're going to have to mess with the solvent, the eluent, to get them to go further if we want to. So, messing with the eluent, messing with the developing solvent, means looking at what our developing solvent is and recognizing that ethyl acetate and hexanes are really wildly different in terms of polarity. This is chapter 1 stuff in lecture. Basically, something that's full of nothing but carbons and hydrogens, i.e. hexanes, is extremely nonpolar, whereas ethyl acetate, with a couple of oxygens in there, the ester functional group, is polar relative to the hexanes. That said, these are both relatively nonpolar compared to the silica gel. So, when I have a plate and I spot my sample mixture on the plate, it's sitting there at the bottom of the plate. Then I develop it, and the spot or spots, if there's more than one component in your mixture, moves up the plate depending on how polar the eluent is. So if it only goes that far when using, let's say, 10% ethyl acetate in hexanes, and I want it to go further, I can get it to go further. Let's say I want to move it up this far. I just need to make my developing solvent more polar, because as I make it more polar, I pull it further up the plate.